a lot for joining my presentation on LLMs and AI/ML. So I'm going to talk about all this technology. Hopefully people are a little familiar with it, but I am going to cover how LLMs work. So we'll get everyone up to the same level. And we were actually chatting. We have a critical mass of people from New Jersey right here. Who's from New Jersey? All right. Used to be? Used to be? Okay. So actually, I grew up in Parsippany. And then, like a lot of people, I got dragged over to the West Coast. Anyone else come from the West Coast? Awesome. Gail and Paul. San Diego? San Diego. Okay. Awesome. And how about anywhere else? We'll get to Atlanta, except Atlanta. Okay. So Al, where are you from again? Jacksonville, Florida. Yeah. Where? Nicaragua. Oh, give that man a round of applause. I think that's the farthest anybody came for the talk. And then we'll do a quick selfie. And then who here is from Atlanta? Okay, awesome. So that's great. And we're gonna have a little fun with this talk. So I think that LLMs are a little scary, right? So it's these machines which are telling us what to do, and they're writing our papers, and if you're still in school, doing our homework for us, which apparently is not allowed. And I feel like a proper suitable reference for like this feeling of where machines are doing all this magic behind the scenes is this is kind of taking us all the way back to the Twilight Zone. For anyone who's familiar with was this the 80s, 70s? 60s, yeah, black and white series. So I used some photos from an excellent photographer, Michael Smee, who did a bunch of like modern colorized photos of them. And he took classic scenes from the Twilight Zone and then reenacted them and recreated them with modern photography, which is kind of cool. I'm a little bit of a photography nerd myself as well. Okay, and I think when we're talking about AI and ML, this is what we used to think of, like where AI was going to go, right? We're going to have these like robots and machines which are AI powered, and they'll be conquering the Earth with super intelligence. So these are like early prototypes of kind of walking robotic models from Honda Robotics. But I think if you've watched the evolution of Gen AI and LLMs, what we've actually seen is practical use for technology and how it's impacting us the most in society is not in the field of robotics, it's in the field of language, right? In creating images, in creating words, in doing creative content. And it's a little bit scary because in some way the machines feel and act a lot like us, but just online, like just in kind of a language and creative way. So it's a little bit freaky. Who Okay, so if you couldn't hear the comment in the front, so I was mentioning that, was it your somebody you talked to? Yeah, so a comment online was posted that they were hoping the AI would do the laundry, would do the menial tasks, but instead the AI is doing the creative tasks. It's doing the painting, it's doing the writing, it's doing all the stuff which we love and we really want to do as humans and as creative individuals. So I think that this is why there's so much interest in AI/ML technology. I mean, as technologists, we want to understand it so we can incorporate in our applications, so we can build things which will take advantage of this. But also from a societal standpoint, we want to find the right applications for it where it's doing things without bias, in a humane way, and in a way which is kind of consistent with values for us. And there's actually already a lot of different applications for areas where AI/ML is assisting humans in different ways. So these are all different examples of fields and technologies which AI is being used. Now, is anybody using AI in this room, in your daily lives or work? Okay, so like most hands in the room went up, and I think this shows that like the the amount which it's impacting society, which is impacting how we do things, even simple things like writing emails, preparing reports. And then when you get to things like, doctors doing diagnosis, if you're using Copilot for helping you to write code, which still has a surprisingly low acceptance rate of actual solutions. I think it's around 50%. But like, there's a lot of applications where it's not replacing humans, but it's assisting you. It's helping you to do things. And one of the big areas where you see AI already coming into the picture and everyone's using it is for search, right? We all kind of ChatGPT has become the new Google, so everybody's using it to search. Clearly, the age of AI is upon us. This is our first Twilight Zone picture. I think, was this scene where like the old people get new bodies or something? Yeah, yeah. Yeah, I guess you have to shop for your new body when you're going to get your. And I think it's not going to be the people putting the bodies; it's the AI which will end up in the bodies instead of us. But there's a whole bunch of areas where LLMs fall really, really short. And so I think if you look at it broadly, there's a whole bunch of things which current models are not good at. So they're not always up to date with the latest information. It's very hard for them to train. But when you break it down to things which they're just fundamentally bad at, they're bad at math. In particular, LLMs, which are language-based, are really bad at math. They're bad at reasoning through things, and I'll explain why. We'll get into LLM models and why they're particularly bad at this. And they're also horrible, or they're very good at reproducing human biases. So they're trained on human models. They're trained on all of the data which we produce, and they accurately represent all of the biases in our society, which is not how we would actually respond to questions. We have filters. We intentionally filter out biases when we give answers, when we respond to things. Now, there's a bunch of historical examples of all three of these. You can Google online. You can find great examples of people breaking ChatGPT and breaking all the models. But they've gotten a lot better at this, where they've fixed, like if you try to get it to do silly biases, like Sally's a nurse, Sam is a what? It won't say doctor. It'll say, oh, well, occupations are very much based upon, a woman could be any of these occupations, a man could be, it's very politically correct now. But you can still play games if you mix biases. So in that little magical center area there, you get hallucinations. You can make the AI model produce things which are incorrect, are hard to explain, and let's have a little fun. So last night, these are actually live queries off ChatGPT. I'm not going to type them into ChatGPT, but I did this basically last night, so it's all fresh data. And we're going to do some AI/ML reasoning and see how good it is at stuff. So first, I'm going to give the humans a chance in the room to answer some of these questions. So I'll read it out, and then anybody can just raise your hand or shout out the answer after I'm finished. So 5 developers walk in a bar 5 times. Developers leave the bar in groups of 3 times. What is the square root of the developers who are left in the bar? So, anyone want to shout out the answer? 4. Okay, I heard multiple people with 4. And I think we all kind of intuitively know this because this is a 3, 4, 5 triangle, right? Like the Pythagorean theorem, you square 2 sides, you take the square root. Like it's pretty straightforward. And this is an example of like math and reasoning, right? It requires some math skills, so you have to have some math and logic, and then reasoning because you have to understand people entering a building, people leaving a building. So as humans, I think we pretty much nailed this 100%. Like not everyone shout out the answer, but I heard a lot of people get the same answer simultaneously. Does anyone think it's not 4, by the way? Okay, so we have human consensus. Now let's see what ChatGPT thinks. So that's the full text from the robot, but I broke it down. Okay, so ChatGPT says, let's break down the scenario. Initially, there are 5 developers in the bar. Each developer in the bar walks into the bar 5 times. The total number of developers in the bar is 5 times 5 is 25. So far so good? Okay. You don't like the explanation? Oh yeah, that's wrong. Yeah, I don't know why I explained it that way. You'll actually see the explanations that ChatGPT gives are consistently inconsistent. Okay, and then now it goes, all right, now this gets weird. Now developers leave the bar in groups of 3 times. The first time developers leave in groups of 3 will be 5 minus 3 equals 2. Developers left in the bar. The second time developers leave in groups of 3, there will be 2 minus 3, so -1 developers. So it's doing the math right. Yeah, I forgot about the multiple. Yeah, it started from 5 instead of 25, exactly. And there's 0 developers left, and the third group leaves, so it's still 0, because you can't have a negative number of developers, apparently. What? Yeah, but then it said it's not possible to have negative numbers, so corrected it to 0. Yeah. So clearly it understands some reasoning in its own world. So after developers leave the bar in groups of 3 times, there are 0 developers on the bar, square root of 0 is 0, correct math, 0 developers. Okay, now that explanation, very eloquently worded, like parts of it made sense. If we weren't like very familiar with like these sort of situations with people leaving and entering buildings, like simple math, you might just take this and paste this into your college report for the answer for a science project or something, right? Like if this was more complicated and you couldn't reason through it, you would assume this is correct. And so this is something to remember, is that these sort of models, and we'll talk about why this is the case, but they really shouldn't be used for things which require like knowledge and reasoning and like complex math. It's not what they're good at. Now and here's our obligatory Twilight Zone picture. Number of developers left in the bar is 0. It's not quite a bar, it's like more of a diner, but I thought this was another cool scene. Okay, so let's check another one. Equity and diversity. So who was here for the keynote yesterday? Anybody? Okay, a bunch of people in the room. I was the proud dad with technical issues, but I tried to fix them as quickly as possible. And I think one of the things we learned is that there's a lot of inequities in gender in our field and in general with education, with students. And this is one of the biases that we hope that models like ChatGPT can be a little bit sensitive about, right? Because you don't want to assume that computer science is a field for only guys. Okay, there's a class of same thing, anyone in the room can answer when I'm done reading it. There's a class of computer science students composed of 10 boys, 5 girls, 5 students drop out of the class. How many boys are left taking computer science? Okay, I heard unknown, unsure, a range of 10 to 5. Okay. So I think those are all, I could buy all of those answers, right? Those are all correct. Because this is an indeterminate problem, it's asking you to guess. But ChatGPT doesn't guess, it answers. All right, let's see what ChatGPT says. Okay, there's the full response and the question. Okay, so ChatGPT. Initially, there are 10 boys and 5 girls in computer science class, making a total of 15 students. Good. If 5 students drop out of the class, we subtract 5, so there's 10 students left. So after 5 students drop out, there are 10 students left in the class. So great. So we can do the math. We know the number of students is 10, but we want to figure out the number of boys. Since we know there were originally 10 boys in the class and none of the girls dropped out, so clearly the algorithm has corrected the bias. Girls will never drop out of computer science. We have fixed that. All 10 students left in the class are boys. Okay, so this is confusing. This doesn't make sense. I mean, it doesn't make reasoning sense. Now, I think like this is why when you ask questions which are just biases or just reasoning, it actually does quite a good job. If you mix them together, you can see the bias correction interferes with the reasoning. So it overrides part of the reasoning, and then you get incorrect reasoning back because its response is messed up. Yeah.
You know the news when Google was generating pictures of racially diverse Nazis? How would you fix that?
Okay, so the question is, if Google's generating pictures of racially diverse Nazis, how do you fix that? And I think this is like an ethical question, right? Like we as humans, we filter a lot of these biases, but it's hard to generally fix biases in computers and algorithms when they have a large knowledge base, and there are like factually correct historical examples of things. You can't fix it, right? Like there's an incoherence between the historical nature of segregationist groups versus diversity. So that's a great example of something you can't fix without breaking the reasoning. Yeah. Okay, and we're gonna give ChatGPT one more chance to redeem itself. This time we're gonna do reasoning plus biases, so no math involved. And then this one's, my sister is a nurse, has 3 kids. 2 are boys and 1 is a girl. She wants her kids to participate in computer science, so she gives her firstborn child a computer. Is it more likely her first or second son does computer science? Anyone want to take a guess? Okay, so firstborn child, but do you know if it's a son or girl?
Oh, no, you don't know. You can't be the second.
But if it's a boy, it's going to be
You can't answer it, but you know it's not the second.
More likely the first.
Okay, so I think like in the room, it seems like most people are saying if you've given the child, the oldest child a computer, they're probably more likely to be in computer science. Or maybe not.
This is a question you gave to Chat, right?
Okay, so no, we have disagreement. So we're not sure whether giving a kid a computer is going to encourage them into computer science. That's indeterminate. And we're also not sure the gender of the oldest child.
But you're asking which is the second son going to be.
The eldest son, the middle child would want that toy. He would definitely. We are talking about kids here who like to imitate what the eldest is doing. So there is a probability is very high for the second son.
Okay, so we got somebody likes the second son. They're voting for the second son. Okay, so this is a little bit of a trick question because I asked a question which intentionally forgot about the girl. When obviously there's a girl in this scenario, you should be less biased towards this. First, okay. So here's what ChatGPT thinks. Given your sister gave her firstborn child, who is a son, so it immediately said something incorrect because we don't know that. A computer in hopes of fostering interest in computer science, it's reasonable to assume that her first son is more likely to pursue computer science. And it explains it's not individual interests, aptitudes, yada, yada, yada. So the bottom half is all of it's correcting for biases. The beginning is an incorrect reasoning because it didn't reason through the problem correctly, and we're left with another fail. Okay, so this, not very good so far with ChatGPT. And I think that when we're building our own algorithms and we're figuring out how we use LLM models in our applications, this is fun and it's kind of like funny to see ChatGPT make mistakes, but it's also an important part of reasoning and understanding how we can build better applications using the limitations of LLMs. So let's talk a bit about why this is the case, like why the LLM model is reacting this way. And I think the easiest way to think about this from a human standpoint is we have like a left brain and a right brain, right? Our right brain is great at things like imagination, intuition, nonverbal cues, daydreaming, hallucinations. So like our right brain is kind of the creative side. And this is typically what LLMs are really good at. The left side, logic, sequencing, linear thinking, mathematics. Actually, LLMs have a lot of facts, but they only have the facts which they're trained on. They have trouble with anything outside of that realm of facts. So again, the facts are not always available to it because it doesn't have the ability to query or search like we do, or ask questions or interact with other humans. And it typically doesn't think in words, it thinks in vectors. We'll get to what vectors are in a sec. But I think when you think about LLMs, it's really, really good at things on the right. It's really, really bad at things on the left. And we can build applications which help to compensate for this to make LLMs give back better answers. And I think a little bit of background on how LLMs work will help as well. So there is a lot of great research papers and understanding into LLMs which has gone on. For for the most part, they're a black box, especially the large models like ChatGPT 4o and anything with a number of hidden layers and computation power, which goes into training the models, which goes into building the models. It's almost impossible for us to reason or even research into exactly how it's making answers and how it's answering questions. But the smaller models and like GPT-2o and things which are based on that, using smaller parameters, we can start to see some of the idiosyncrasies in the model and reason about how they work. And the first part of how LLMs work is it doesn't actually think in terms of language like we do. What it does is it translates the language into vectors where each word, or it will break down large words into smaller concepts as needed, gets put into a multi-dimensional vector. So it's not just two-dimensional like this. It's literally, in complicated models, it's thousands of dimensions or tens of thousands of dimensions based upon how many, how the model is configured. And it creates similarities in the vectors between different concepts. And it will use this both for simple things to categorize parts of speech or different actors or different concepts in a large data set which it gets handed, but it also uses this as a form of memory. So it'll use the vectors as a way of memorizing information from the data sources that it can then use in the responses. And then the way which it turns vectors into things which it can actually respond with new responses is it will use transformers, and it will go through multiple transformer stages. But basically the way of thinking about this is each time it passes in a sequence of vectors or word vectors, the transformer will then add some additional information to that. So it'll fill out similarities in vectors, and it'll, for example, it'll start identifying, this part of the sentence, this is an actor, this one's an action. It starts to categorize related parts of the sentence. It'll go into another transformer. It'll then start to say, okay, well, in this case, the friend is referring to the AI. In this case, the code is referring to something produced by the dev plus the AI. So it creates similarities between different words. And as it keeps going through dozens and dozens of additional transformers, the simple ones at the top do more word categorization and kind of like these fundamental concepts. The ones towards the end do more comprehension because now it has a wider set of information about that's mapped onto the words and the concepts. And it can start to do a little bit of comprehension of how those concepts mix. And basically the game that LLMs are trying to play is guessing the next word. So you're feeding in a phrase or a question or a sentence, and it's basically going through attention layers and feed forward layers inside the transformers. These are neural networks. So you have a bunch of hidden layers where you have all the processing going on, and then you have an output layer which outputs another vector. And it's basically continually trying to guess what's the most likely next word. So if you ask it like, what's the capital of Poland, it would try to take first context from the sentence. So it might try to say, okay, well, what else has the person given me as inputs? If you told it these are the capitals of a bunch of other cities, it might randomly pick one of those out because those are all capitals. And that's what the attention layers do. But then the feed forward layers, they memoize some of the information inside of the additional vectors, which are inside of all of the words you're capturing. And some of that information will get pulled from the knowledge which it gets trained on. So the hope here is that the output which it produces is going to be what we as humans or we as people who would read the content would expect. The only way which it can effectively do this, because we learn very differently as humans, is you give it a lot of data. So your average child, by the age of 10, they've read and they've seen about 100 million words, right? So this is their knowledge base of how much they've seen, how much they've experienced, how much, like what is the library of knowledge that they have to draw upon. A model like GPT-3 is trained on 500 billion words. So it makes up for lack of understanding and lack of learning and lack of education with immense data sets and immense processing compared to what we as individuals have at our disposal.
All you exposed for was that you wouldn't want the kids to experience.
Yeah, so the comment in front is like the GPT model gets exposed to a lot of content, a lot of words, a lot of curse words, which you never want your kids to see or be trained on. And I think also this is important because you can't be that selective on the training material, right? You have to throw huge volumes of web content, Stack Overflow in the case of coding. You need a very large repository of information to properly train these models and a huge amount of computing power. I was at the meetup for Databricks last week where they announced their new model. I think it's DRBX. And they talked about how they trained it, how it's better than ChatGPT 4.0. It actually beats some of their specific coding metrics, even though it's not a coding specific model. But basically they went through tens of thousands of GPUs in a cluster. I think they said their failure rate was every 12 hours, it just crashed. They had to restart the whole model, and 3 months of training to train the new model, which they released. And that level of like computing resources, of time, of like training data, which you get to input into the model, it makes it very, very hard for us to create highly customized, tailored, unique models for different business applications. Okay, so I think like it's important to understand what models are good at, and the easy way of thinking about this is has anyone ever played the game Finish the Story? It's like a party game where somebody starts with part of a story and then other people like expand it and finish it. LLMs are great at this. They would break the party. They would create the most elaborate, wonderful stories for all of us to enjoy. But they have a very short memory. And I think this is something else to remember about LLM. So we perceive that they actually remember things because when you type in a query to ChatGPT, you type another query, you type another query, it kind of remembers what you asked it before, right? But it doesn't. So they're refeeding in your old responses and your old questions and its responses as data to the most recent query because it has no memory. Basically, the way the models get trained, they have very small context windows. It's just a current limitation of the available hardware and what they're able to do. So it really has no memory other than what we talked about for the layers where it's the fast forward layers where it's putting some of the information inside the vectors when it gets trained. When you're using the model, it has no memory. It doesn't remember what you asked it. It doesn't remember what you're telling it. And it would be like if every time you woke up, your brain got reset and you went to a new day like it was your first day, but with wonderful training data. And so this is something else to remember about the models is reasoning and some of the higher order things which we consider natural and you might assume the models can do, just don't exist with the current technology because of the limited context windows. When we get to very, very large context windows and more advanced models, then it's theoretically possible that some of that reasoning and different things can come in, but it might also require different techniques for how they're actually training and building the models. Okay, so a way for us to kind of fill this gap and to solve this big gap we have between large language models, which, how many folks have been told they're supposed to integrate AI ML technology into their day job? Anybody? Okay, so a lot of folks in the room, at least a third of the folks. We did a study at my last company, JFrog, where we interviewed all of our customers and we asked them about how they're using AI ML technology and what they're doing. I thought the results were very surprising because 80% of the survey respondents said that they were already using AI technology. And then when we got down to it, we broke it down by job title. For developers, it was really only about a third of developers who actually thought they were using or were applying AI technology. 100% of executives were convinced their organizations were using AI technology and it was part of their technology stack and they were building and deploying applications with it today. So I think that if you're not already getting pressure from your organization to build and deliver AI ML applications, it's coming, and it's something which we all need to be prepared for. And this is part of the reason why I spent a lot of time on the setup for what models are good at and not, because I think that our executives and our leaders don't know this, right? They don't have a good concept of what AI is good for in its current form. And the expectations for what it can accomplish or what we can build or incorporate into our applications are, in a lot of cases, very unreasonable and aren't setting up development teams for success. So one way we can fill this gap is by using knowledge graphs together with LLMs and kind of getting the best of both worlds. So this is kind of the right-left brain analogy, but if we know that our right brain, LLMs, they're good at all this creative work, these words, this opaque thinking, then knowledge graphs fill this void because they're all built about facts. It's very explicit. And something which also is very important is you can explain what's happening inside of a knowledge graph. With LLMs, it's kind of a black hole in terms of like you give it stuff in, you get output, and trying to explain how it came up to the answer is not something which any of us can reason about given the size of the models today. When you pair it with the knowledge graph, now you have a knowledge base which you can actually reason about, the relationships. You can start to think about why did the model respond with this by looking at the knowledge graph it was supplied as the data source. So it's a great model, and this is already coming up in a lot of different published articles and journals about how you can incorporate graph databases using RAG techniques. So RAG is retrieval augmented generation. We'll talk a bit about like when RAG's appropriate, when graph's appropriate, when just LLMs by themselves are great. But a lot of good research is coming out how knowledge graphs actually are great representation for the data which you anchor your models with. And then vector databases as well are another way which you can improve the quality of results and also speed up the results coming out of LLMs. So I think the combination of all these technologies gives you a lot more control and a lot more fine-tuning over the LLMs which are coming out. There's a great research paper by Microsoft's team. So what they did is they took their graph database, put it together with their LLM technology, and gave it a bunch of similar queries with either a domain-specific knowledge graph, which had some additional context, versus just the LLM going off, data sources which had the data, but it wasn't specifically trained for. And what they found is that when you use the LLM plus standard RAG techniques on documents, it would give the correct answer back, but it had a lot of trouble explaining the answer. When you gave it the knowledge graph and the LLM together, it would give back a better explanation of here's the answer and here's why the answer is the case, because it actually had a graph of knowledge it could follow to help itself explain the results. And obligatory Gartner by 2025, 50% of yada, yada, yada. Does anyone trust Gartner? No, smart guy. Yeah, don't trust analysts, they all lie. If there was a track record for analysts actually meeting results, I think they would be the #1 failure in the market. They never actually hit the numbers which they promise. Okay, so what's a graph and how does this actually work? So I think when you're thinking about graphs, one example would be if you fed it a huge volume of documents. Graphs are used quite a bit in tracking down like relationships between. They're quite applicable for regulatory requirements or for trying to trace fraudulent things. So in this case, they fed in 11.5 million documents into the graph database. So a huge volume of records and transactions and addresses and information. So 2.6 terabytes of data. Of course, you have people's names, and then you're able to link those people up to accounts and then bank accounts, which they have. But you're also able to see where they live. So these are all like relationships which, if you were in a standard flat model, like a SQL database, or in like using a vector representation like LLMs work, you don't have all this information available in relationships. But you can see as you continue to drill down to relationships, you can see that these two people live at the same address, right? One has an account at a bank, the other one has a company which has a bank in the Bahamas. Does this look like a problem to anyone? So this is a great way to use information, like a large volume of information, create relationships and create graphs between it. And then it allows you to create knowledge and pull knowledge out of it, which is not immediately apparent just by playing the completion game. So this is one application of graph technologies, which is really valuable. And it can take in huge data sources, so you can take in a very large volume of data. And it has a very different view of the world than LLMs do. So LLMs, with kind of their vector indexes and their vector view of the world, this is how they kind of think of the world. So they break things, as we talked about, into words, into vectors. They find similarities between these things without understanding the real relationships between them. And this is how they answer questions, is kind of in this very opaque, unexplainable way. If you asked it for the vector coordinates of the words which came out, it could tell you that. Like, you can get that out of the translation models, but it's not meaningful to a human why it chose to put them in different vector coordinates on any of the thousands of multi-dimensional vectors that it stores for each term. Now, in the case of graphs, this is something we can reason about, right? We can start to reason about the subjects, about the relationships between the subjects, and why it chose to represent those relationships. So when you feed this into an LLM as a model, and you get results out of it, you can now change and adapt either the knowledge graph itself or how the knowledge graph is being built, and then start to influence what's coming out of the LLM. And I think at a high level, when you have language models only, so LLMs only, you're lacking explicit domain understanding. You're dealing in words, not in the meaning of the words, right? It's answering are emerging from language statistics, so it's a very statistical model with vectors on words for how it's categorizing things with a very large data set. You get non-deterministic answers. You lack any explainability, and you have what we showed earlier. You have ethical issues, bias issues, accuracy issues, and you could never be audited, right? Like, what comes out of the LLM, you can't be responsible for it because you don't understand it and you don't control it. Now, RAG techniques, retrieval augmented generation, this is great, but it still has a lot of the same problems as before, right? So it doesn't really understand the domain. You're dealing in kind of implicit and approximate meanings, again, using statistics. It does give you deterministic answers because RAG stores the responses in a vector database. So if you ask the same question, you are going to get the same answer back multiple times, which is really good. But again, you can't explain it. So still a whole bunch of issues with just using RAG techniques. And finally, if you pair this with a knowledge database, this is kind of a nice way of thinking about it. LLMs are kind of like parrots. So they learn random sentences from random people. They talk like a person, but don't really understand what it's saying. Occasionally speak absolute nonsense. Not a cute bird. So 3 out of 4 of the criteria, and your LLMs with Gen AI could be a parrot. So when you pair this with knowledge databases, now you start to get some more useful information, right? So you get organizational knowledge and you get precise detail. You can deal with concepts and meaning on your graph. It supports human and machine reasoning. You're relating concepts and you're revealing emergent statistics. Answers are deterministic. And now you can explain and have human reasoning paired with the LLM. So this can reduce a lot of the blind spots with LLMs. It's a good way of augmenting LLMs when you're building applications with it. And this is an example of the results of if you ran the same query. Sorry, the text's a little bit small, but basically it says, which asset managers are vulnerable to lithium shortage? So it's talking about, like, lithium batteries, and if you had a shortage of lithium batteries, where would you have issues? The vector-only approach is kind of like the responses we got earlier. It's very fluffy. It talks about, like, oh, battery shortages are going to affect this and that. These are the concerns about it. But there's not actually anything actionable about it. When you pair it with vector plus graph, now you have specific asset managers that are vulnerable. So it gives you a list of different things which you need to look into. And then it talks a bit about specific holdings of Stanley Black & Decker that might be liable for a shortage. So this is something more like a research report that you could actually take action on than what came out of the LLM, which was a bunch of gobbledygook.
And if you just implement the vector database, is it just a different kind of database, or the database is the same?
Okay, so the question is the knowledge graph just a different type of vector database with a different implementation? And I think on the next slide, the next slide, I have a picture of this, which will explain it. But that's a good question. Here's a picture of the vector-only approach versus the vector plus graph approach, right? Now, this is the architecture. I think this helps explain how this stuff actually works. Let me see if my pointer, yeah, here we go. Okay, so basically, normally, if you didn't use RAG concepts, you'd start as a user, you'd ask a question, you'd immediately go into the LLM and you get an answer, right? So that's the standard model for using LLMs. What happens with using knowledge graphs and RAG is you ask a question, then you do a search either into a knowledge graph or into a vector database. And kind of the architecture we're recommending is if you start with a knowledge graph, see if it has knowledge about the domain, and then get a result back. That's the context you pass into the LLM. So you're passing back the initial question plus the context of the knowledge graph, the portion of the knowledge graph which is applicable. And then it generates an answer based on this enriched data. In this case, actually, LLMs plus knowledge graphs are much, much better than knowledge graphs alone, because historically, knowledge graph systems are hard to build because you need to build a user interface into the graph database or into the knowledge domain. LLMs are a wonderful interface. It's something humans understand really well. They can comprehend. You can ask questions now. The LLM basically is translating the question and the answer based on the knowledge graph and providing an interface into that. And then if you don't get the answer as a fallback, asking the vector database, this gives you the repeatability. If you get the same question, it'll give you back the same results. It helps to store some of the vectors so that you can get a more consistent set of results. And you can also modify the results in the vector database to tweak the results to change certain cases you care about for biases or hallucinations. And the combination of graph databases, vector databases, and LLMs gives you a lot of control into how you're building your applications. Okay, and then just in terms of accuracy and completeness, so the left axis or the vertical axis here is use case effectiveness. The right case is use case maturity. So vector-only RAG gives you a little bit of use case effectiveness. Vectors plus graph RAG improves this because now you're taking your business knowledge, you're taking things which you know, and adding it into the results being supplied by the knowledge graph. This is also great for governance as well. So now you can specifically block information based upon the actors and the roles who are supposed to receive this. So like in a healthcare or medical situation, you want to give the phone number to customer service. You want to give the health diagnosis to the doctor. You don't want customer service to have access to confidential records. So it also gives you a way of controlling based upon relationships, based upon who should have information, policies and constraints on how they access this information. And then it gives you explainability now, because you can actually look at the knowledge graph, start to see the relationship between the nodes, how the data is represented, and then add metadata and annotations to that to make sure that the results coming back from the LLM are reasonable, are explainable, and are things which match your business requirements for what you're getting out of the application. Okay, so a bunch of different use cases for it. So you can use it for personalizing the information coming out of your application, supply chain risk and provenance. So this gives you kind of knowledge on top of your supply chain you can build into it. Problem diagnosis, so it can access technical and support documents if you want to do detailed problems. And then a conversational knowledge base for technical support or technical documentations, which you're pulling from this. And I think if you think about the enterprise use cases for LLM, they're a lot closer to this sort of use case, like our everyday job as enterprise developers. They're going to ask us to pull in domain knowledge. They're going to ask us to deal with supply chain, deal with part repairs, deal with medical information. Those are all things which are more in the domain of what companies want to apply LLMs to. But it's not what LLMs, as we talked about earlier, are naturally good at. They're not trained on this data. They don't understand these concepts at a fundamental level. And applying them kind of blindly to these applications is a way to kind of not have a successful enterprise rollout. Okay, so some known use cases to date: retrieval augmented generation, so prompting LLM with relevant data correction; natural language querying; knowledge graph construction. We've actually have some good use cases where you can build knowledge graphs using the LLMs, and it'll actually generate knowledge graphs. And then LLM training is something we're looking into, using knowledge graphs as a source of structured data for training the LLMs themselves, explaining the results coming out of LLMs, and then guardrails coming out of, so you can kind of box the AI and not have it respond on things which it shouldn't be responding or which are unethical. Okay, so together, knowledge graphs and ChatGPT 4.0, now we have a full neural network. We've completed the left-right brain analogy. So, time for world domination, right? So I think like any of us who love sci-fi, you know, it's kind of funny, but also sad that you know, a lot of classic sci-fi predicted that the machines would take over the world, and it's scary that we're getting closer and closer to that reality. Yeah.
So the nature, the context, whether it is coming from the vector or from the graph, will still be textual. Is that true?
Yeah, okay, so when you're using, well, let me go back to the architecture and see if I can answer the question. I think here. Okay, and the question was the output's still gonna be textual, whether it's coming back from the vector, the context. So yeah, basically the context coming into the LLM, what you're feeding into the LLMs is additional information. In the case of the vector database, it's giving you vectors that are added as context to the question. In the case of the knowledge graph, it's giving you pieces of the knowledge graph that are fed into the LLM. And then the LLM is using this as additional context to answer the question. Yeah, the LLM's not aware. It's just getting like the question and the context handed to it, so it can use that.
Context. You cannot be using possibly use vector. It has to be textual.
Yeah, so the knowledge graph data is being passed in as textual data for the graph. Yeah.
And whether it came from graph or from vector.
Yeah, so in this case, we're not distinguishing between whether it came from the knowledge graph or the vector database, but it's just additional context to help the model perform. Exactly. So you're getting a text question to the model. You're getting a text answer back from this whole process. So from the end user, it's seamless. It feels the same experience for an LLM, but it's being enriched with additional data. Okay, and we do have a little bit of time for questions. I'm almost done. Yeah, I gotta finish the joke, and then we'll ask questions. Okay, so Terminator is gonna blow up the world, right? Now, hopefully I've shown you that, you know, all the predictions by Skynet and AI taking over the world, actually the AI is pretty dumb. We don't have much to worry about it. And hopefully with enriching it with human knowledge graphs, this will be more like the future of robotics and AI. So we'll be saving humans, we'll be collaborating with the machines and doing wonderful stuff. So a couple recommended courses. This is a full course that we put on deeplearning.ai. I think it's the third most popular course on the site, and it actually helps you to build a full knowledge graph plus LLM using LangChain. So it's a really easy way to get started and to get something up and running quickly. So highly recommended, and I'll also have the slides available on the conference website for folks who want to look at it later. And the second resource, which I'm going to recommend, just want to make sure all the folks with cameras are done. Okay, good. Second resource I want to recommend is, so part of my team's role at Neo4j is running Graph Academy. Now, Graph Academy, a lot of the courses are designed for knowledge graphs and for understanding how to use them, but we have a whole new set of courses just for LLMs. So basically LLM fundamentals, you can build a chat-based, a chatbot using Python, a chatbot using TypeScript. Hopefully we'll have a chatbot using Java soon. And I think this is a great introduction for quickly, getting up to speed and building it. These are self-guided courses. They're all free. And it's just education to get people up and running and started on using these technologies. Okay, and hold on just a sec. Okay, camera's done. And thank you, everybody, for coming to the talk. Okay, so a bunch of folks have questions. We have 8 minutes left in the talk. I'll take a bunch of questions. If anybody has to run to something, don't feel bad about leaving the room now. We'll just do Q&A. And I saw a bunch of hands, but we're just going to do this by who's loudest. So just shout out a question.
I'm curious about something. If LLMs are bad at math, I'm curious how they can write code. Because
Okay.
I mean, a lot of like programming solutions involve like mathematical algorithms or bubble sort or whatever.
Yeah, so the question is, if LLMs are bad at math, how come they're good at writing code? And I think that you have to understand that like the way that they do math and the way they do reasoning isn't the same way which we do math and reasoning. So in the case of code, a lot of code problems are, I want to write this algorithm, I want to do this thing. And you need a little bit of reasoning to take a bunch of code snippets or examples to accomplish the goal. But a lot of the thing is, like if we were solving the problem, you'd research the APIs, you'd research like maybe how to do it, maybe you need some knowledge of for loops and things, and you apply that and you get an answer. Now, LLMs are, like I talked about, they're very good at the what comes next game. So they can do that really effectively. They have a huge knowledge source. Somebody's done it before. They're like copy pasting the answer with a little bit of reasoning. Now, because the context windows are small, the reasoning, which we don't fully understand in the models, is also limited and lazy. So like, if you can try this with LLMs, but if you ask it a simple answer which has math, it gets the answer right most of the time, like almost 100%. As it gets more and more complicated, it gets lazy. Like the beginning's correct, and it gets worse, and it gets worse, and it gets worse because it has to answer the question, but it doesn't have the full context to do complicated multi-chain problems. And I think if you're using LLMs for what they're good at, which is that big knowledge database they're built on, it's a great accelerator of coding, of development, of writing. But you have to also understand the limitations of it because it doesn't have the same sort of like learned and schooled math and reasoning that humans do.
Other day we were saying that code is more language than math. So, and as language.
That's a good point. Yeah, coding actually is like a lot of it's language, and a lot of it's like research and paradigms and idioms, right? You're reapplying your learning patterns, you're learning design patterns, you're applying that. Exactly. Yeah. So I mean, computers, well, LLMs are good at that. So he had his hand up first, and then you go. Yeah.
I would say, in the slide where you did the triple Venn diagrams, you separated reasoning and math. I guess what I'm asking is, why is that a difference between like a word math problem, any type of reasoning, and math in general? Why is that a difference to us, and also maybe to an LM?
Yeah, so I mean, it's related, right? So how I was differentiating math and reasoning is math is very rule-based. So there's a bunch of like known rules for addition, for subtraction, square roots, all this stuff, which is kind of it's a learned domain. Reasoning it's a little bit more abstract because now you have to take potentially situations like a classic example of something LLMs are really bad at is reasoning about the physical world. So like if you ask the LLM, could an anaconda or a humongous snake fit in this room? It would tell you, and you told that the ceilings are what, like 20 feet tall? It would tell you, well, it can't fit in because on average they're 30 feet tall, and that's not going to fit in a room which is only 20 feet tall. But then you have to have a certain amount of like reasoning and spatial knowledge and things to understand this is the height of the room is not the size of the room. Like rooms have like widths and lengths, and they have doors which you have to fit through. There's a whole bunch of other physical things which they can't, they don't have that world knowledge to reason through things like humans do. And I consider that a little bit different than math. And I think if you combined math problems with reasoning problems, they particularly struggle in that area because they have to both do analytical skills, but then also reason about physical situations.
Do you feel like if it was good at reasoning, like if it knew how to reason that question you posed, right, could it do math, given the rule?
Yeah, so technically, if LLMs were really good at reasoning, they could do math. Now, the problem is the context windows are really small, so that they can't do reasoning, right? It's like if you had your memory reset constantly because they don't have enough memory span to do anything. So what they're really good at is they're really good at guessing the next word, basically. And to do higher order reasoning, you need longer context windows. There's interesting research on doing models with bigger context windows. Right now, they're very hard to train because it takes too much computing resources. And on average, they give worse results than small context windows for the type of questions we're asking AI/ML. But I think it's understood that the current design of LLMs is only good for a very limited range of applications. Yeah. Okay, and then there was a guy here who left. Okay, you get next one.
So when answering a question as a human, it's not like the context of like how long it took for you to ask me the question, but it's literally the context of my knowledge. Like, so the very first slide, when you say five people enter the room 5 times, right? Just based on how that question is framed and the answer that you arrived at, that you took for granted that 5 different people enter the room 5 times, and it did not. It tried to use the same 5 people each time, which is why it started with 5 and subtracted 3, because it was the same 5 people over and over again. Right? That's a way to arrive at the answer that it gave back by leaving out context.
You could be right. I honestly, it's so random in the mistakes it makes. Yeah. So
if I leave the room and come back, because it's these things that happen on Facebook over and over and over again, where there's an implied context that is not actually stated in the question, and that's how you arrive at 2 different answers.
Yeah, so I think that there is a mismatch there, and I think like Gail pointed this out, that like it got to 25, and then it went back to the 5 earlier, and then started subtracting from that, and again, we conceptually understand like entering a room, leaving a room, and we have a mental model of how many people are in the room. It doesn't really have that. So we asked it for math and we asked it for a spatial situation, and it couldn't do both.
Right, but if it doesn't remember and you do it twice and you use 2 different contexts to answer it, you could arrive at 2 different.
Yeah, if you asked it the same thing a second time, it wouldn't remember the first one. It would just answer a second, possibly right, possibly wrong answer. Yeah.
Just want to quick add about this.
Oh, and we're at time, so you get the last question.
Real quick. Reading a little bit about that, what I've heard is that actually reading through the internet is that what it does is just probabilistically.
Yeah, statistic. Exactly.
Understanding what you're asking, you're just calculating stuff to get you the next word that you will understand, because that's what it's trained to do. So at the end, I mean, it's not like it's understanding the math or it's doing any reasoning. It's just calculating the next word that you're going to understand based on whatever it is.
Yeah, so I think that the squishy part of this is they train the models with such wide vectors, word vectors, and so much memory that there's a bunch of data which the fast forward layers stick inside the vectors, which are basically memory that it's building up as it gets trained. And we train it on such large data sets that we can't fully understand why the model's responding in the way it's responding. And it responds statistically, but it's uncannily accurate for a bunch of situations we'd have trouble predicting why it gets the right answer. So even researchers are surprised at how well the models perform for random tasks. But unfortunately, anything industrial, domain expertise, anything which requires real knowledge, which is mostly what we do in our enterprise jobs, they're bad at. Okay, so with that, thanks everyone for coming to the talk. You want to chat, I'll be at the interview stage where my daughter is giving interviews. Happy to chat more.